Let's try this.
Okay. So this is what we're doing now.
That's good. Right. That's right. Good.
And I don't want to touch this carbonyl.
That's right. You might even want to put an asterisk there to remind yourselves that's going to be the carbonyl. That's looking good. I think that shows some good progress. That was basically the same thing as acid-catalyzed transesterification, but that gave us a lot fewer hiccups there. All right. So how many protonations did we have here total? How many times did someone pick up a proton? Who picked up protons here?
Twice.
Yeah, who picked up protons?
The initial L and
the carbonyl oxygen, and then the L. We protonated the carbonyl oxygen, and then we protonated the L. Why did we protonate the carbonyl oxygen?
To make it a better electrophile.
So it's logical that immediately after we did that, the nucleophile attacked. Okay? And then why did we protonate the L group? To make it into a better leaving group. And it's logical that immediately after we protonated our L group, remember, who's the L group? It might have been a good idea to label it at the start. This is the L group, because it's easy to lose track of it once the reaction started. This is the L group. Why did we protonate that L group? Well, to make it into a better leaving group. So it's logical that immediately after we protonated it, it left. And of course, we've actually seen that sometimes we can have a leaving group that just is not protonated here, but you can't do that under acid conditions. Under acid conditions, this has to be protonated before it leaves. Otherwise, we generate a negative intermediate. So we really had to protonate this first before it could leave. And then there had to be 2 deprotonations. So who deprotonated here?
Well, in the internal proton transfer.
Yeah, and who deprotonated there? The original nucleophile, right? Because after the nucleophile attacks, it ends up with a positive charge, so it makes sense that this deprotonated immediately after it attacked.
You had said the leaving group didn't leave because it'd be OET minus an acid, right? That's what you said?
That's right. We can't have this guy leave until he protonates, because that would give us that negative charge. So immediately after the nucleophile attacks, it has to deprotonate, and we showed him deprotonating and simultaneously protonating the L group as our proton transfer. And then who else had to deprotonate?
Very end.
The carbonyl oxygen to reverse the original, because again, we want to, the whole point here is to attack the carbonyl, but eventually reform it. So we have to take that back. Yeah. And then we regenerated this over here. So again, we had a hydrolysis. What type of functional group did we start with here?
Ester.
Yeah, and who attacked the ester?
Water.
Water. This was water attacking an ester. That's why this is called hydrolysis, right? Because it's water attacking. And what type of functional group did we produce? What functional groups did we produce?
Carboxylic acid.
Carboxylic acid and an alcohol. So it's important to see that we produce the carboxylic acid here. Remember, that again is why esters are called carboxylic acid derivatives, because when you hydrolyze them, they give you carboxylic acids. All right, so this was our hydrolysis. The water basically broke this bond. And again, it's important that you know this mechanism, but it's also important that you're able to go straight from here to the products. And the reason why that's important is because in the exam, you're going to see some problems that involve, say, 5 hydrolyses. And he doesn't want you to do all the mechanisms, he just wants you to do the hydrolyses.
So they're derivatives specifically because of the hydrolysis, the effects from hydrolysis, correct?
The definition of a carboxylic acid derivative is, a carboxylic acid derivative is something that when you hydrolyze it, you produce a carboxylic acid. Anything that when hydrolyzed produces a carboxylic acid, the convention is that those are called the carboxylic acid derivatives. So we've seen that an ester is a carboxylic acid derivative because when we hydrolyzed it, we did produce a carboxylic acid.
Okay, thanks.
That's the reason why all of these things are carboxylic acid derivatives. You can see that when you hydrolyze any of these, it will give you a carboxylic acid, because what are we going to replace the L group with? Well, we'll replace it with water, which will, after it deprotonates, will give you a carboxylic acid. Again, it's easy to look at this and forget that this came from water, because it's deprotonated, but this originally came from water before it deprotonated. What happened to its other proton? It got stuck onto the leaving group over here, basically. So again, the important thing is, it's important to convince yourself that you could have gone straight from here to here without doing the intermediate steps. Well, you put a squiggle across the bond that's being hydrolyzed. It's the bond between the carbonyl and the L group, and you just break that bond, and then you ask, what do I do with my elements of water? Well, the OH replaces the L group, and the hydrogen gets stuck onto the leaving group. And that's how you can do the hydrolysis in one step without having to go through the whole mechanism. And again, this is important because on the exam, you'll see problems where he doesn't want the mechanism. He wants you to do 5 hydrolyses in a row, and then he just wants you to show the hydrolyses.
Just sort of quick.
Yeah, because for example, you'll be doing a protein problem where he'll give you, say, 5 amino acids that are all connected to each other by amide bonds. And then he's just going to do hydrolysis, and he wants you to hydrolyze all those bonds. So you'll see what I mean in a second, or in a week or so. Anyway, it's important to know the mechanism, but also to go from here to here.
Okay, and amides are totally different? Or can we...
Yeah, amides would be very similar reaction, but maybe before we do that, we should do the base-catalyzed reaction for hydrolysis, because that's very important as well. What we've done here is acid-catalyzed. The base-catalyzed actually has 1 or 2 little hiccups that we haven't seen before, so.
Okay.
But it should be shorter than the acid-catalyzed. All right, so we want to do an so we've got the acid-catalyzed down. All right, so what would be the starting materials for base-catalyzed hydrolysis here?